The runway stretched beneath the early morning haze at Heathrow. BOAC Flight 712, a sleek Comet 4B, set poised for departure, engines humming with restrained power. The flight deck lights glimmered against polished instrumentation, each dial a guardian of complex systems. Outside, ground crews moved methodically, unaware of the minutes that would come to define the crew's lives. At 7:03, the aircraft began its roll. Thrust leapt forward, tires shrieking against asphalt, the acceleration measured yet urgent. Within the cockpit, the captain and first officer followed standard takeoff checks. Flap set, engine parameters monitored, radio contact maintained. Everything appeared routine. Seconds after liftoff, a subtle anomaly emerged. Engine number 2, the port inboard unit, registered a slight overtemperature warning. A quiet tension settled over the cockpit, a signal invisible to passengers, yet critical to trained eyes. The crew began diagnostic steps. Engine instruments flickered, oil pressure dips and temperature spikes suggesting an unfolding problem. Below, the suburban sprawl of West London passed unnoticed by those inside the cabin. Passengers adjusted to the climb, the aircraft ascending smoothly toward its cruising altitude. Outside, a low cloud ceiling loomed. Inside, the first hints of smoke seeped into the cabin venting system, a faint acrid scent. Cabin crew exchanged glances, trained instincts whispering caution. The minutes stretched, taut with suspense. Every decision in the cockpit now carried weight beyond routine procedure. The aircraft, its systems, and the crew had entered a precarious threshold where mechanical anomaly could quickly cascade into crisis. BOAC Flight 712 was no longer merely departing. It had become a study in human judgment, engineering resilience, and the unforgiving logic of physics. The tension was invisible but absolute. The flight was about to confront its defining moment, one that would challenge every safeguard designed to prevent disaster. By 1968, BOAC, British Overseas Airways Corporation, was a carrier at the forefront of transcontinental aviation. Its fleet was modernizing rapidly, and the Comet 4B represented both technological ambition and the lingering lessons of early jet operations. Introduced in the mid-1950s, the Comet series had been the first commercial jet airliner, pioneering high-altitude flight in pressurized cabins. The 4B model combined increased payload capacity with structural reinforcements following prior accidents, yet vulnerabilities persisted. BOAC Flight 712 was scheduled from London Heathrow to Sydney, with intermediate stops, staffed by a crew that included Australians, reflecting the airline's integration of Commonwealth personnel. The captain brought decades of experience, a steady hand forged in both piston and jet aircraft. The first officer, relatively younger, was meticulously trained on Comet systems. Cabin crew included members with prior long-haul experience, attentive to both passenger comfort and emergency protocol. Collectively, the team embodied professional aviation standards of the era, trained to mitigate predictable in-flight anomalies. The aircraft itself, Comet 4B GRWE, was a jet of 114 seats, powered by 4 Rolls-Royce Avon turbojets. Its fuselage and wings were aluminum, riveted and pressure-tested, and the fuel system incorporated multiple redundancies. Engines were prone to localized overheating if improperly maintained or monitored, a vulnerability well understood in BOAC's technical manuals. Fire detection was rudimentary by modern standards. Temperature sensors and crew observation were the primary safeguards. There were no automatic fire suppression systems in the wing route, a limitation of contemporary design. Environmental conditions that morning were standard for London: low cloud layers, light winds, and visibility sufficient for visual navigation. The air traffic control environment at Heathrow was busy but orderly, with multiple simultaneous departures and arrivals. Aircraft separation procedures relied on precision timing, and strict adherence to standard departure protocols. Beyond the technical and operational framework, the human dimension cannot be overlooked. Flight crews in 1968 operated under high-stakes pressure, balancing commercial schedules with emerging jet technology. Australia-linked crew members carried cultural ties, communication styles, and training experiences that influenced cockpit dynamics subtly but meaningfully. These factors, though invisible to passengers, would play into decision-making during the unfolding emergency. The stage was set: a modern jet, experienced crew, standard weather, and a departure into the unknown. The machinery and humans were competent, yet even small deviations, a rising engine temperature, a missed maintenance cue, or a delay in emergency recognition, could cascade into critical outcomes. BOAC Flight 712 was departing as a testament to progress, yet inherently vulnerable to the latent hazards of early jet aviation. Understanding BOAC Flight 712 requires a multifaceted examination. The aircraft, its crew, the surrounding environment, and its systems together created the framework within which the accident unfolded. Each element was individually competent, yet their interactions under stress revealed vulnerabilities inherent in 1960s aviation. Aircraft. The Comet 4B represented the pinnacle of early jet design but remained constrained by the engineering of its era. Aluminum construction, while lightweight and strong, conducted heat rapidly. A fire originating in an engine nacelle could spread to the wing root before detection. Fuel tanks were integrated into the wing structure, separated by bulkheads and valves intended to isolate leaks. Engines were mounted beneath the wings, with access panels designed for maintenance but not rapid inspection in flight. Rolls-Royce Avon turbojets delivered impressive thrust but were sensitive to lubrication and temperature management. Even small deviations in operating parameters, overheating, oil pressure dips, or unrecognized vibration, could escalate quickly. Fire detection relied heavily on pilot observation and cockpit sensors. Smoke ingress into the cabin ventilation system often served as the first real alert to crew. Fire suppression existed in the engines, but the Comet's wing root remained vulnerable to rapid flame spread, a critical weakness given the limited automation of the era. Crew. The flight deck team included a captain seasoned in both propeller-driven aircraft and early jets, a first officer trained rigorously in Comet operations, and cabin crew experience in passenger safety. Australian-linked crew members contributed both operational skill and cultural nuance, discipline, communication style, and adherence to protocol that would shape coordination under pressure. The human factors of this crew were a study in procedural rigor. Decisions had to balance immediate technical assessment with passenger safety, prioritizing containment, landing options, and evacuation logistics. Training emphasized checklist compliance, but the speed at which the fire escalated tested the limits of procedural response. Cockpit resource management in 1968 relied more on individual initiative than on standardized CRM practices developed later. Environment. Heathrow's early morning conditions were technically benign: low cloud cover, light winds, and clear visibility. Yet the airspace was dense, with multiple departures and arrivals. Aircraft separation required strict timing, leaving little margin for extended troubleshooting or holding patterns. Once airborne, the aircraft entered a low-cloud deck, reducing visual references and increasing reliance on instrumentation. The subtle combination of weather, airport traffic, and limited emergency airspace compounded the challenge of an unfolding mechanical emergency. Systems. Flight 712 systems reflected 1960s jet engineering. Hydraulic controls managed flight surfaces, electrical systems powered instruments, and pneumatic lines supported environmental controls. Engine temperature warnings, oil pressure gauges, and vibration sensors provided early indicators of abnormal operation, but interpretation required immediate expertise. Emergency checklists existed for engine fires, yet real-world response was constrained by the speed of the developing hazard. Smoke detection in the cabin and cockpit was rudimentary. No automated fire suppression existed in the wing route. The interaction between mechanical limits and human action defined the crisis trajectory. The engine fire escalated faster than the systems could contain it. Crew response, though competent, was constrained by training norms, time pressure, and incomplete information. Passengers, largely unaware, were exposed to risk primarily through procedural timing, evacuation speed, exit accessibility, and coordination. By examining these angles together, a pattern emerges. The accident was not a single point of failure but a cascade. Aircraft vulnerability, environmental factors, system design limits, and human procedural constraints converged, creating a scenario where rapid escalation became almost inevitable. The story of Flight 712 is as much about the complexity of modern flight as it is about the bravery and professionalism of those tasked with managing it. Shortly after takeoff, Flight 712's engine number 2 began to deviate from normal operating parameters. Oil pressure dropped subtly, and temperature readings rose past recommended limits. In the cockpit, the captain noted the anomaly, following standard procedures, monitoring instruments, cross-checking readings, and preparing for potential shutdown. Within moments, smoke entered the cockpit ventilation system, thin, acrid, and unmistakable. The crew initiated the engine fire checklist. Thrust was reduced, the affected engine shut down, and fire handles activated to cut fuel and hydraulic supply. These steps were textbook, precise, and deliberate, but the fire had already begun to spread into the wing route. Heat transfer through the aluminum structure and proximity to fuel lines accelerated the situation beyond the speed of standard countermeasures. Cabin crew noticed a faint smell of smoke filtering through the ventilation vents. Passengers, still settling into the climb, remained largely unaware. The captain contacted air traffic control, requesting an immediate return to Heathrow. Controllers cleared the flight, directing a rapid descent toward the nearest suitable runway. As the Comet approached the airport, flight instruments reflected the growing complexity of the emergency. Hydraulic pressure fluctuated, and cockpit visibility was partially impaired by smoke. Pilots coordinated descent, speed, and flap settings carefully, aware that structural integrity could degrade if speed or angle exceeded limits. Each adjustment was measured, each decision weighed against the consequences of both fire and emergency landing. Landing was executed at high urgency but with disciplined control. The aircraft touched down with engines carefully managed, braking applied progressively to avoid stress on the wing structure. Once on the tarmac, the evacuation sequence began. Cabin crew, trained for rapid response, opened exits and guided passengers in a controlled, methodical flow. Some doors required manual override. Slides were deployed under smoke-laden conditions, yet panic was minimized through crew presence and procedural discipline. The fire, now reaching the inboard wing, caused localized structural failure, producing smoke and flames visible outside the fuselage. Emergency services arrived promptly, dousing flames and supervising passenger safety. Miraculously, most occupants escaped with minor injuries, a testament to the professionalism and coordination of both crew and emergency responders. Flight 712's accident sequence illustrates a critical aviation principle. Rapid escalation can outpace both human response and mechanical safeguards. The chain of events, from initial engine anomaly, fire propagation, procedural response, to controlled evacuation, demonstrates the interplay of engineering limits, human judgment, and environmental constraints. No single failure caused a near catastrophe. Rather, it was a cascade of factors, each manageable in isolation but collectively decisive. Once Flight 712 came to a halt, the immediate crisis transitioned into systematic response. Emergency crews secured the aircraft, extinguished the fire, and oversaw passenger evacuation. Injuries were minor for most, but the potential for catastrophic loss had been undeniable. In the hours and days that followed, attention shifted from survival to understanding. How could a routine takeoff escalate into a near disaster? The investigation was led by the British Air Accidents Investigation Branch, AAIB, tasked with reconstructing both mechanical and procedural factors. On inspection, the team confirmed that engine number 2 had suffered a catastrophic internal failure, producing intense heat and smoke. Metallurgical analysis revealed that high-temperature stress and material fatigue had contributed to the rapid spread of the fire. Investigators also focused on the aircraft systems. The Comet 4BS fire detection and suppression mechanisms performed within design limits, but their scope was insufficient for the wing route scenario. The AAIB noted that the redundancy of fuel shuttle valves and fire handles was appropriate, yet the structural materials and fuel distribution allowed rapid escalation, highlighting a design vulnerability that would influence future aircraft engineering. Crew performance underwent rigorous review. The captain and first officer followed the prescribed emergency checklist with precision. The investigation emphasized the importance of human factors. Clear communication, adherence to procedure, and calm decision-making significantly reduced potential casualties. Cabin crew actions were similarly scrutinized and praised. Their training ensured orderly evacuation despite smoke and urgency. The broader impact extended beyond Flight 712. Media coverage, measured and factual, framed the accident as a testament to professional training and robust procedures rather than sensational spectacle. Aviation authorities and manufacturers examined the incident to identify systemic improvements, enhanced fire detection in wing structures, fire-resistant materials, revised engine maintenance protocols, and refined crew emergency training. Flight 712's accident became a case study in aviation engineering and human factors. Its lessons informed both aircraft design and operational protocol worldwide. Designers reconsidered engine placement, fuel system routing, and fire containment measures. Airlines revised training to stress rapid recognition and containment of engine fires. Emergency procedures incorporated insights from the evacuation sequence, improving efficiency and reducing risk for future flights. Ultimately, the investigation demonstrated that accidents are rarely the result of a single failure. Flight 712 illustrated the convergence of mechanical stress, design limitations, and environmental variables, mitigated by disciplined human action. The aftermath was not merely technical analysis, but a roadmap for safer skies, emphasizing preparation, redundancy, and the professional execution of emergency protocols. BOAC Flight 712's near tragedy became a turning point in aviation safety. Its lessons were absorbed quietly but profoundly, shaping procedures, training, and aircraft design for decades to follow. The most immediate legacy was procedural. Airlines worldwide revised engine fire checklists, emphasizing rapid recognition, engine shutdown, and situational awareness. Crew training increasingly incorporated simulation of wing route fires, smoke ingress, and rapid evacuation sequences. Lessons from Flight 712 highlighted that while mechanical failures may be unavoidable, the disciplined response of trained personnel could prevent disaster. Engineering also evolved. Aircraft designers examined engine placement, fuel system routing, and wing structure materials. Fire-resistant alloys, better insulation, and localized suppression systems became standard considerations. The Comet 4B incident reinforced a guiding principle. Redundancy alone was insufficient if critical systems could be compromised faster than human or automated response. Emergency evacuation procedures were also transformed. Flight 712 demonstrated that orderly, controlled evacuation is possible even under smoke and stress. Cabin crew protocols were refined, slides and exits redesigned for reliability, and passenger instruction emphasized clarity and calm compliance. Beyond technical and procedural change, Flight 712 reinforced a cultural lesson within aviation. Professionalism, preparation, and adherence to procedures save lives. Every decision made in those critical minutes, from engine monitoring to passenger guidance, was a demonstration of human skill counterbalancing mechanical failure. Aviation authorities codified these lessons, embedding them in regulations, training curricula, and aircraft certification processes. Today, the incident is often cited in safety manuals and training modules. It serves as a quiet reminder that aviation's progress is measured not only by technological milestones, but by the discipline and judgment of those who operate aircraft under stress. The legacy of Flight 712 is not spectacle but insight, that systematic analysis, continuous improvement, and professional rigor transform near tragedy into enduring safety. As the Comet 4B lifted from Heathrow that morning, the potential for catastrophe existed, yet the coordinated actions of crew, the resilience of design, and the precision of emergency response prevented the worst. The story closes not with dramatics, but with reflection, a testament to the quiet vigilance